At Rescue Education, we have the best explanation every time. I'm Dr. B, and I'm going to help you easily and rapidly learn organic chemistry. If you like this video, you'll love my self-help books. Learn more about them at rescueedu.com. Our second topic in stereochemistry is how to assign RS configurations using the Cahn-Ingold Prelog rules. The configuration of a chirality center is the actual spatial arrangement of the groups attached to it. Enantiomers have opposite configurations. We often need to know exactly which enantiomer we have, and we need to be able to specify it clearly. The Cahn-Ingold Prelog rules are the correct way to assign the configuration of a chirality center. This is the system used in the official IUPAC naming rules. There are 3 steps to assigning configuration. First, assign priorities to each of the 4 groups, with A being highest and D being the lowest. We'll see the rules for assigning priorities on the next page. In step 2, we reorient the molecule to look down the carbon D bond, so D is hidden. This is an eye looking down the bond, and this drawing shows you what the eye would see. A is on top, B is on the right, and C is on the left. In step 3, we assign the configuration. If priorities decrease in the clockwise direction, the chirality center is R. If priorities decrease in the counterclockwise direction, the chirality center is S. There's no simple way to figure out this pattern for R and S, so you just have to memorize it. There are several rules for assigning priorities to the groups attached to a chirality center. The most important rule is that atoms with higher atomic weight have higher priority. In this simple example, the halogen atoms can be ranked from iodine, which is the heaviest, to fluorine, which is the lightest. The priorities go from A for iodine to D for fluorine. We manipulate the molecule to put fluorine the farthest back. We choose to hold the chlorine and to do a piano stool rotation of the other 3 groups. In practice, you just have to put the lowest priority group, fluorine, the farthest back of all the groups. You don't actually need to hide it behind the chirality center. Once we do this, we label each atom with its priority, and we see they decrease in the clockwise direction. This molecule is the R enantiomer. The second rule is that if 2 or more atoms directly attached to the chirality center are the same, and in organic molecules this is usually 2 or more carbons attached, then you systematically compare the atoms in each group, layer by layer, until you reach a point of difference. This molecule is the S enantiomer because the priority decreases in the counterclockwise direction. How did we assign priorities? Hydrogen is always D if it's attached to a chirality center because it has the lowest possible atomic weight. The hydroxyl has the highest priority because it has a heavy oxygen, which is directly connected to the chirality center. It gets A. But the other 2 groups have a carbon directly attached. How do we decide which is B and which is C? The first layer in each is a carbon. The second layer of atoms in the left-hand group is carbon, carbon, hydrogen. The second layer of atoms in the bottom group is carbon, hydrogen, hydrogen. The left-hand group wins and gets B because it has 2 heavier carbons. The other group has only 1 carbon. Notice that the very heavy bromine atom doesn't matter at all because it's beyond the layer where there's a point of difference. The third rule is that groups with multiple bonds are treated as if they had the equivalent number of single bonds. So a generic double bond with atoms C and W is treated as if it had 2 CW single bonds to each atom. A triple bond is treated as if it had 3 CW single bonds to each atom. This CC double bond is converted into 2 single CC bonds at each carbon. This CC triple bond is treated as 3 CC single bonds at each carbon. The terminal triple bond wins over the T-butyl group. When we treat the terminal triple bond as 3 single CC bonds, we get this pattern. Now carefully compare layer by layer. At the first layer, both are carbon. At the second layer, the triple bond has 3 carbons, and the T-butyl group also has 3 carbons. At the third layer, the triple bond has 2 heavy carbons and a hydrogen, but the T-butyl group has only hydrogens. The triple bond wins at the third layer. Pause and try these sample problems. Assign the correct RS configurations to the following molecules. In the first problem, we want to put the lowest priority hydrogen atom back relative to the other 3 groups. So we can hold the bromine and then rotate around the bottom. Bromine gets A because it's the heaviest atom. Ethyl wins over methyl because ethyl has an extra carbon. So ethyl gets B, methyl gets C, and the groups go down in priority in the counterclockwise direction. So this is the S enantiomer. In the second problem, we also want to put the hydrogen back relative to the other 3 groups. So we'll hold the isopropyl group and then spin around the left-hand side. This puts the vinyl group up and the methyl group forward and the hydrogen group back. So hydrogen is D. The vinyl group is treated as if each carbon had 2 carbon-carbon single bonds. Let's put in all the atoms so we can see all of the layers clearly. Let's draw out the isopropyl group too so we can clearly see all the atoms and all the layers. Of course, the atom in the first layer for both groups is a carbon. In the second layer, the vinyl group has 2 carbons and a hydrogen. In the second layer, the isopropyl group also has 2 carbons and a hydrogen. In the third layer, the vinyl group has 1 carbon and 2 hydrogens. But in the third layer, the isopropyl group has only hydrogens. So The vinyl group wins because it has that carbon in the third layer. The vinyl group is A, the isopropyl group is B, and the methyl group is C. So priorities decrease in the clockwise direction. So this is the R enantiomer. The configuration of a chirality center in a cyclic molecule is easiest to assign if the lowest priority group, usually a hydrogen, is pointing back. The process works best if we look down on the flat molecule and have groups pointing up and down, as we do here. This molecule has two chirality centers, which are both S. How did we assign these configurations? Let's assign the right-hand carbon first. It's already set up with the hydrogen back. The hydroxyl is A because it has a heavy oxygen atom directly attached to the chirality center. How do we assign the other two groups, which are both part of the ring? We go systematically around the ring. We see at the second carbon, the left-hand group wins because we hit a methyl group. The bottom group has no extra carbons attached, so it loses and gets C. The priorities decrease in a counterclockwise direction, which means the center is S. To assign the other chirality center, I like to flip the molecule over to put the hydrogen back. The other three groups all have a carbon directly attached to the chirality center. You should be able to see that methyl is the lowest priority and gets C. It has only hydrogens attached to the carbon. The left-hand group wins and gets A because you hit a hydroxyl at the second carbon. The bottom carbon has no extra substituents at the second carbon, so it loses and gets B. Again, priorities decrease in the counterclockwise direction, so this center is S. If you're using my book, I encourage you to do the extra test your knowledge problems for this topic, so you can be sure you really understand it. All the answers are at the back. This video is closely based on my first semester organic chemistry self-help book. My self-help books are particularly valuable in difficult learning situations, but you can also use them to get an edge or to get a head start. If you want to learn more about my books and videos, how to get the books, or my future projects, go to rescueedu.com.